Hello everyone, my name is Aladdin Shaoub and I'm a PhD student at the Université de Lorraine, and today I'm going to present to you our recent work titled Towards Interpreting Deep Learning Models for Industry 4.0 with Gated Mixture of Experts. This is a joint work with Christophe Cerizara, Alexandre Voisin and Benoît Jung from Université de Lorraine. This presentation is divided into four sections. First, introduction and motivation of the subject. Second, experimental setup and proposed approach. Third, results and discussions. And finally, the conclusion. Interpretability has become very crucial in the recent years, as we are using more and more AI-based models in our daily life to automate our decisions. So we need to make sure that these decisions follow the same safety and ethical rules as we do. Also, now the European Union allows people to have the right of explanation. So AI solution developers need to make models more interpretable. In the literature now, there are two major approaches to achieve interpretable models. The first ones are passive approaches or post hoc, where we try to interpret an already trained models. The second ones are active approaches, where we actively change the network architecture or the training process to get a better interpretability. In this work, we are interested in the second ways of achieving interpretability, and more specifically, the approach is based on the gated mixture of experts. This system has been around for 3 decades. It consists of a gated network that selects which expert to be used depending on the input. We are interested in this type of interpretation because we want to interpret models based on the concepts present in the data, which means that we want data that are coming from the same expert to be treated by the same experts. This will make it easier for us to understand how the model operates and how to debug it. This approach seems promising. However, the majority of the current work does not focus on applying this system for interpretability. And those who do, they use this system as a model on its own, which means that they assume that the concepts or the tasks are handled by the whole model, which is not always the case. Also, current work rely on the change in the architecture alone, which leads to a pathological case called module collapse, or the problem of low diversity in expert usage. We get this case when the gating network tends to converge to a state when it always produces large weights for the same few experts. This imbalance is self-reinforcing. When favored experts are trained rapidly in the beginning of training, they will be more and more selected by the gating network, and thus the gap will increase, resulting in poor interpretability. In this work, we are addressing these two research gaps by inserting the gated mixture of expert system as a sublayer in a larger state-of-the-art neural network for Industry 4.0, and also by proposing a way to incorporate expert knowledge as a constraint during training the model to help reduce the problem of module collapse. Now, let's go to the experimental setup and the proposed approach. In a previous work, we proposed this model based on an MLP-LSTM-MLP architecture to predict the duration between the current time and the time when an equipment no longer performs its intended function. This value is also known as the remaining useful life of equipment. So it's a regression task. With this model, we were able to achieve state-of-the-art results, so we wanted to make it more interpretable with respect to the operation conditions. An operation condition is a circumstance under which a system operates. So, in our case, the operating conditions are considered as the concepts that in the data that we want our gating network to consider them as subtasks. As I said before, the first step is to understand which part is responsible for dealing with the multiple concepts in the data. In our case, the part responsible for dealing with the varying operating conditions. By investigating the learned representations, as you can see in the right of the figures in the right, we remarked that the first MLP in the architecture is the part we were looking for. On the figures on the right, on the x-axis we have the sensors or the input features. On the y-axis we have the time or the cycles, and on the z-axis we have the values. As we are trying to learn a function that maps degradation, because we are trying to model the degradation of equipment, we can see in the figure below that the signals from the input do not manifest any degradation pattern, and this is due to the varying operating conditions from cycle to cycle. But the output of the MLP in the figure above we can see degradation clearly. So the first MLP is the part handling the varying operating conditions. This is why in this work we replaced only the first MLP with the gated mixture of expert system. In this case, a perfect interpretability means that the gated network should be able to assign each operating condition to an expert. Now let's get to the questions we faced while trying to implement the approach. First, how many experts should we use? Because sometimes we don't know the number of concepts present in the data. In our case, the number of operating conditions. The second question is how to deal with the problem of low diversity of expert usage or model collapse. For the first question, we did two experiments. The first one is with the correct prior, meaning we use 6 experts because we have 6 operating conditions. The second experience where we have a false prior, so we don't know the number of operating conditions, or we are using just an arbitrary number of experts. And in this case, we use 9 experts, even though we have 6 operating conditions. The goal of these experiments is just to know if this is indeed a problem, or we can achieve the same results with a correct or a false prior. For the second problem about the model collapse problem, we added a term to the loss function that encourages expert usage to follow a prior distribution that we know. By minimizing the mean squared error between the frequency distribution of expert usage with the uniform frequency distribution in our case. Now let's get to the results. Here I show only the results using only a change in the architecture without changing the loss function. And this is just to highlight the problem of model collapse. We have a pretty big figure, so I will walk you through them before talking about the results. The x-axis over all the plots represent the number of experts actually used by the gated network, or in other words, the number of clusters predicted by our gated network. Also, we have two columns, A and B. A represent the results from the case where we use 6 experts in the architecture, and B when we use 9 experts in the architecture. And this to answer the first question we asked before. And we have 3 rows. The first row shows the histogram of the number of predicted clusters over 20 experimental runs. This is just to evaluate to see the variance of the results. The middle row shows the mean and the standard deviation of the normalized measurable information between the predicted clusters and the operating conditions. This value is the one we are using to evaluate the interpretability performances of the approach. The bottom row shows the root mean squared error on the test data and to compare the results with the state of the art. The green rectangle represents the mean and the standard deviation of the state-of-the-art root mean squared error from our previous work. Now let's get to the actual results. From the first row, we remark that in more than 87% of all runs, only 1 or 2 experts are actually used. This is what we referred to as the problem of model collapse before. Also, we remark even when we predict a number of clusters that is relatively close to the real number of concepts present in the data, like 4 or 5, the value of the normalized mutual information drops. So just as a small conclusion, relying on the architecture alone will not lead to high interpretability, because there is nothing forcing the gated network to get out of the self-reinforcing problem. Now let's see the results for the case of adding the constraint value to the loss function. We observe that mostly 3 clusters are predicted regardless of the number of experts used in the architecture. They better match the operating conditions with the value of the normalized mutual information close to 0.7. We also note that as the number of experts used increases, the value of the normalized mutual information also increases in a logarithmic way, unlike in our first experiment without any constraint. Which means that training with this constraint encourages the model to decompose the data in an interpretable way, even more when the number of experts used is high. Furthermore, the number of predicted clusters is not larger than the number of operating conditions, even when we are encouraging the model to use all 9 experts. As for the predictive performances of the model, we remark that they do not vary much across conditions, and the values of the root mean squared error are very close to those of the state of the art, represented by the green rectangle. Finally, we note that changing the strength of the constraint in this case does not result in a significant change in the model interpretability or performances. So to wrap up, in this presentation we talked about the idea of inserting the system of the gated mixture of experts as a sublayer in a larger neural network for interpretability. Also, we propose to add a constraint to the loss function based on external knowledge to enhance interpretability. And finally, we showed that for this particular case, having a correct or false prior do not change the results dramatically. That's all for this presentation. If you have any questions, send me an email, and thank you for your attention.